About a subject called optimization, I'm going to start with what's called the open top rectangular box problem. Okay? So here's how it works. You have a piece of paper or cardboard with given dimensions. So let's pretend this is sort of like a standard piece of paper. So it's 8.5 inches wide and 11 inches long. Okay? And what we're going to do is we're going to create a box out of this thing by cutting squares out of each of the corners. Now I'm going to make the squares congruent. So here's what I plan to do. I'm going to go down to this corner. I'm going to cut a square out of the corner. That's not a very good looking square. Let's fix that a little bit. There you go. And then over here I'm going to cut a congruent square. So this square and this square, these two squares on the bottom have the same dimensions. And so does this one up here and this one up here. Okay? And then the next thing I'm going to do is I'm going to fold along these green lines. So if I do that, I'll end up with a shape that looks like this. Okay, and just so we're clear on things, the green lines I folded along are now along the bottom here. There's one in the back, okay? And then the sides of the squares, well, they met up along these vertical lines. Okay? And then I'll highlight in blue these blue line segments now become the top edge of the box. So the question is, what size squares should we cut out? So for example, I think you can imagine that if I wanted to, I could have cut a bigger square. So when I started with my original rectangular piece of paper, instead of cutting squares like I did here, I could have cut a bigger square. Maybe I cut something out that was a little bigger. Okay, and if I'm going to use 4 congruent squares, then this happens. All right, not a perfect picture, but you'll have to tolerate it. Now you can see the green lines I fold along give a different shape. Well, not a different shape base. It's a rectangle. But it's certainly a smaller rectangular base here in this bottom cut scenario than in this top cut scenario. Right? And then the box I get as a result over on the side won't be as wide along its base. But it will be taller because the side of the squares I cut out is taller. So I'll get a box like this. So let's sort of match up the colors and make sure we can see everything. So here's the green. Here's the green rectangle on the bottom. This green rectangle is that green rectangle. Here are the top edges that come together to form this top edge. And then lastly, those dotted red lines, here they are. There's the dotted red lines right there. Okay? All right, so it's not a beautiful image, but it does the job. The question is, what size square should I cut out of each of the corners so that the box I create can hold as much stuff as possible? Imagine I was going to fill that box with M&Ms or something that I really wanted to have, and I wanted to have a lot of that. You know, what size square should I cut out of the corners to create a box that can hold the most amount of stuff? So the first thing you should try and convince yourself of, or trying to make a decision about, is, does it matter even, right? Maybe, do you think maybe that these two boxes, we'll call this box number 1 and box number 2, do you think that they hold the same amount of stuff? Right? Now, while we're at it, we should have just mentioned, what are we interested in? We're interested in volume, right? Volume would measure how much capacity a three-dimensional object has, the whole thing. So do these two objects have the same volume? That's sort of what we're interested in. Okay. So let's consider one more case that'll help us answer the question, do you think these two boxes hold the same volume of stuff? So I'm going to draw one more rectangle, and I want you to imagine an extreme case. Imagine the case where I cut a super tiny square out of each corner. Okay? And then I fold it along these green lines. This would be helpful if I was a better artist. Okay. It's the last time I'll criticize myself. That's it. And what do you get now? Well, if you look at the shape you get on the side, you get a pretty wide box, but it's super short, like this. Okay? Now, if you think about it, I've been using the example of putting M&Ms in here. If you're going to put M&Ms in this box, it looks like you just put like one layer of M&Ms, and that's it. So you really wouldn't be able to fit a lot of M&Ms in here. I think at this point, maybe you should start to think, hey, I don't think this is a good way to go, that it matters what size square I cut out. Okay? So especially over here, look at this one. This box number 1, for example, yeah, it's a little more narrow, not quite as long, but you can stack many layers of M&Ms in here. Right? So this area of the base gets multiplied many times as I stack more and more layers of M&Ms. In this case, while there's a bigger area of the base, I only get to multiply it by 1 because only one layer of M&Ms is going to fit in there. Okay? Think of volumes like stacked areas. So the question now is, what I said originally, what size square should we cut off the corner of our box to generate an open top rectangular box to get the maximum volume? Okay. So let's start to think about this. See if we can use a little algebra to help us out. Okay. So here are the squares we're going to cut out. Here we go. Okay. And we're going to fold along those green lines. And we agree that we can cut out different size squares. So that's where the variable is going to go. I'm going to call this distance x because I know I can vary that. I can cut out a really small, tiny square. I can cut out a moderately sized square or a big sized square. And then there's lots of x's in other parts of this picture. Here they all are. Okay. Now, let's remember our original dimensions. Our original dimensions of our piece of paper, 11 inches by 8.5 inches. Okay? And then we're going to get a box when we're done. So let's think about that box. That box that you get, my claim is we can name all the dimensions of this box in terms of x. So for example, we know that after we fold it up, that the side of the square becomes the height of the box. So the height of the box is just x. Okay? Now, let's go for this side right here. How long is that? Well, if we match that up with its corresponding side over here, we know this whole distance is 8.5. But clearly that's not 8.5. But 8.5 minus this x minus this x would do it. So this is 8.5 minus 2x. Good. All right, so similar reasoning will tell you that this side here then is 11 minus 2x. And now we have an expression, or we can get an expression for volume. The volume of a box like that is length times width times height. Or in our case, 11 minus 2x times 8.5 minus 2x times x. So what we have a function that tells us the volume of the box depending on how big of a square we cut out of the box. Now, before we go trying to graph this and figure out where its maximum is going to occur, let's just talk about what x can and can't be. So could x be as big as we want is the question I want to ask. And the answer is no, it can't be, because remember, this piece of paper is only 8.5 inches wide, right? So if I tried to cut a square that was more than halfway across, there wouldn't be enough left on the other side for the square that's going to be over here. So that means that x has to be less than 4.25. And obviously, we've got to cut some kind of square out, so we're going to make it greater than 0. So that's our domain for x. All right. So what we're going to do now is we're going to graph this thing and see what it looks like. So we're going to go to y equals, and we're going to type this function in, get rid of whatever's there. So what do we have? Open parenthesis, 11 minus 2x, close open, 8.5 minus 2x, close, times x. Now, I recommend do times x, because if you're using a T89 in particular, you could have a problem. We'll discuss what it is, but to make sure you put times x. Hit enter there. Oh, that looks like an 85, actually. I got to fix that. Looks like I didn't do 8.5. Go back and fix that. Okay. We'll do second insert and decimal. Good. Okay, that works. All right. Now, in terms of our window, we can go to our window right away, and we can change x max to 4.25, because we know we can't cut out a square any bigger than that. In terms of y max, we really don't know what it's going to be yet. So I would just leave it at, I guess, leave it at 10 for now, because this is typically what's going to happen. Most of you are going to have it where you can't tell what the graph should look like or what window you should use, although the graph I just had was pretty good. Press graph, and let's see. And you don't see much. It's like, oh, I don't see anything. And you're not sure where everything is. So my advice is press the trace button, which on a T89 is F3. And if you do that, you notice your y values are up in the 59, 60 area. We got 60.9, 61, and 62, 63. So I have y's that are all in the 60s. So I'm going to go back to window, and I'm going to go to y max. And I guess 100 might be reasonable. Don't go too big. We'll try that to start and see what that looks like. Press graph. Okay, this is pretty good. So now I can see my volume function, right? And it tells me the volume as a function of the size of the square I cut. You can clearly tell that there's a maximum value here that we're going to want. So you do second calculate. You go to maximum. Number 4. It's going to ask for a left bound or a lower bound on the T89. Lower means left. To move left of where the high point occurs, hit enter 1 time. It's going to say right bound or upper bound. Move right of where the maximum is occurring, hit enter 1 time. And it might ask for a guess. Don't worry about that. Just hit enter. And here we go. It turns out the optimal length square to cut out is a square whose side length is 1.585 inches. And if you do that, you'll get a maximum volume of 66.148 inches cubed. Time to look at this from a spreadsheet point of view, right? Well, there it is, Microsoft Excel. Let's open that up. Okay, and let's make it a little bit smaller and talk about this spreadsheet. So spreadsheets are really a pretty handy tool. You can do some nice things with them. So here's what we're going to do. I'm going to make the first column the length of the side of the square. Okay, that's a long title for that column, but whatever. It'll be fine. Okay? Now, would you agree that once we pick that the rest of the shape is determined? Right? We know how long the box is going to be and how wide the box is going to be. So the length of the side of the square, I don't know what that's going to be. That's going to be some numbers. Here I'm going to put length, but I mean length of the box. Okay? So that's that. And then this is going to be the width of the box. Oh. Okay? And then we'll just actually going to simplify this. W and L. And then finally the volume, because that's what we're going to be interested in. The volume. All right, so now what am I going to do? Here, I need to put some numbers. So sort of the smallest thing we could cut out might be 0 maybe, right? You don't cut a box at all, cut a square at all. In that case, you're not going to have any volume. Then maybe we'll go up by 0.2s, right? 0.4, 0.6, sort of a fun thing that Excel can do. If you highlight all these things and you go to the lower corner here, it turns into a plus sign. It will notice a pattern. See that? Pretty neat, huh? Now we know I don't have to go much further past 4.2. So there it is. It filled it in for me. Now, to get the length is equal to 11 minus 2 times whatever's in this cell. Enter. Okay? And the width is going to equal 8.5 minus 2 times whatever is in this same cell. There you go. And then finally, the volume equals this times that cell times that cell. But you'll notice it indicates the cell's name, C2 and so forth. And then actually nothing else. Hit enter, and there you go. Now, I would like this to just happen for me many times, and I can do that just by highlighting all these things. Go to Edit, Fill, Down, and there you go. Quickly calculated them all. And what do you notice? Look at the volume column for a minute. We'll bold all that. And you'll see right around here, somewhere between 1.4 and 1.6, we start to see the biggest volumes, right? Now, we know the right answer from the graph was about 1.585. So we could do that if we want. But this is a quick way to get a good sense of what's happening.